For centuries, we thought the Great Red Spot was just a storm, a big, red, ancient storm on Jupiter. But when NASA sent spacecraft to look inside it, what they found was not a storm in any way that we understand the word. So, let's go inside. The Great Red Spot is the largest anticyclonic vortex in the entire solar system. An anticyclone means it spins in the opposite direction from what you might expect. On Jupiter, in the southern hemisphere, that means it rotates counterclockwise, with a period of roughly 4.5 Earth days. It sits at about 22 degrees south of Jupiter's equator, locked in place between two incredibly powerful jet streams. One flows eastward to its south, the other flows westward to its north. And the spot just sits there, wedged between them, unable to drift north or south. Trapped, but still spinning. Its winds peak at around 430 kilometers per hour. That is roughly 3.5 times faster than the strongest tornadoes on Earth. And unlike anything on our planet, there is no surface underneath this storm. Jupiter is a fluid world. The storm simply keeps going because nothing tells it to stop. Now, here is the first strange thing. We have been observing this storm since 1831. That gives it at least 190 years of confirmed continuous existence. But there is a deeper question buried in the history books. In 1665, an Italian astronomer named Giovanni Cassini observed a dark feature on Jupiter. He called it the permanent spot. An English scientist named Robert Hooke may have seen it a year earlier, in 1664. For nearly 50 years, astronomers tracked this permanent spot, until the last recorded observation in 1713. Then it vanished. No one saw it again for over a century. When a new spot appeared in 1831, at almost the same latitude, everyone assumed it was the same storm. It seemed logical, same location, same behavior, same planet. But a study published in 2024, led by planetary scientists in Spain, used computer simulations and historical measurements to challenge that assumption. Based on the differences in size and motion between the two features, the team concluded that the original permanent spot most likely disappeared sometime between the mid-18th and 19th centuries. The Great Red Spot we see today is a different storm, a younger one. So the storm we have been calling ancient may only be about 2 centuries old, which raises an uncomfortable question. If the first one died, will this one die too? The team ran computer simulations to understand how the current Great Red Spot might have formed. The leading theory is wind instability, a disruption in Jupiter's powerful jet streams that produced what scientists describe as an elongated atmospheric cell. Over time, that cell evolved into the tight, coherent vortex we observe today. It was not born as a single dramatic event. It grew, it organized, it became what it is now through decades of gradual atmospheric self-assembly. For most of human history, the Great Red Spot was just a smudge in a telescope. Beautiful, yes, but scientifically opaque. We could see its color, we could watch it spin. But we had no way of knowing what was happening beneath those clouds. That started to change in 1979. The Voyager 1 spacecraft flew past Jupiter and captured the first detailed images of the spot. Cloud features as small as 160 kilometers across became visible. The swirling complexity was staggering, but even Voyager could only see the surface. Voyager carried an instrument called the Infrared Interferometer Spectrometer, which allowed scientists to sense temperatures in the atmosphere. What it revealed was the first real clue about the Great Red Spot's inner nature. The spot was cold, colder than its surroundings. Its core was a low-temperature anomaly surrounded by a warmer ring. This confirmed that it was a high-pressure system, an anticyclone, where air rises in the center and sinks around the edges. But the Voyager data also hinted at something peculiar. The storm did not appear to be symmetrical. There were subtle differences between the north and south sides of the vortex. At the time, the instruments did not have enough resolution to confirm this. It was filed away as a curiosity. Then came Galileo, The spacecraft arrived at Jupiter in 1995 and spent 8 years orbiting the planet. Its instruments confirmed the cold core structure and mapped temperatures across a range of altitudes. The temperature inside the Great Red Spot was typically about 3 degrees cooler than the surrounding regions. Not a dramatic difference, but enough to sustain a vortex of that size. In December 2000, Galileo captured high-resolution thermal images of the turbulent area northwest of the spot, a chaotic region where Jupiter's jet streams collide with the vortex. This region, known as the Great Red Spot Wake, showed lightning, actual lightning storms confirmed by the spacecraft's instruments. And within that wake, Galileo detected something that no one had seen before on Jupiter: ammonia ice clouds. Fresh condensate lofted high into the atmosphere by violent convective updrafts. So we now knew 3 things. The Great Red Spot was cold, it was deep, and it was actively churning material from below. Galileo also revealed something about the dark lane surrounding the spot. Around the vortex, there is a ring of low cloud opacity, a darker band where the atmosphere appears to be subsiding. At 5 micrometers, this ring glows brightly, because the lack of high-altitude clouds allows thermal radiation from deep in the atmosphere to escape. This subsidence zone acts as a moat, isolating the Great Red Spot from the surrounding belts and zones, keeping its chemistry and dynamics self-contained. Then in 2000, the Cassini spacecraft passed by Jupiter on its way to Saturn. Its composite infrared spectrometer provided broader wavelength coverage than anything before, and it detected something the earlier missions had disagreed about: excess phosphine inside the Great Red Spot. Phosphine is a molecule that forms deep in Jupiter's atmosphere, where temperatures and pressures are extreme. Finding it at high altitudes above the spot meant that air was being dragged upward from the deep interior. Cassini also confirmed the north-south asymmetry that Voyager had hinted at. On the north side of the spot, temperatures were slightly cooler and chemical abundances were enhanced. On the south side, the opposite was true. The storm was not symmetrical. It had a lean to it, but we still did not know how deep. In 2016, NASA's Juno spacecraft arrived at Jupiter, and this time, the mission was designed to do something no spacecraft had done before: look beneath the clouds. Juno carried a microwave radiometer, an instrument that could detect heat radiating from deep within Jupiter's atmosphere. Because temperature increases with depth on Jupiter, different microwave frequencies correspond to different altitudes. It was, in a sense, like sticking a thermometer into the planet at 6 different depths. When Juno flew over the Great Red Spot during a close approach in July 2017, passing just 8,000 kilometers above the cloud tops, the radiometer revealed something remarkable. The roots of the storm extended to at least 240 kilometers below the visible cloud layer. That was as far down as the instrument could see. But the storm kept going. To probe even deeper, scientists turned to gravity. As Juno flew over the Great Red Spot, the massive concentration of atmospheric material within the storm slightly altered the spacecraft's trajectory. These changes were extraordinarily subtle. We are talking about velocity shifts of 1/100th of a millimeter per second, detected by tracking the spacecraft's radio signal from over 400 million miles away. The gravity data revealed that the Great Red Spot extends no more than about 500 kilometers below the cloud tops. That is 50 to 100 times deeper than Earth's oceans. Now, that number might not sound impressive on a planet the size of Jupiter, but it means something profound. Whatever is powering this thing, it is not being driven by solar energy or simple weather processes. The Juno data also showed that the vortex is warmer at its base than at its top. The temperature rises from around -170 degrees Celsius at the cloud tops to well over 200 degrees at the bottom of the storm. That temperature gradient is significant. Temperature differences drive winds. And this warm base may be the fundamental engine that keeps the Great Red Spot alive. Juno also discovered something unexpected about Jupiter's overall atmospheric structure. The belts and zones that give Jupiter its striped appearance undergo a transition about 65 kilometers beneath the water clouds. Above this level, the bright zones are cool and the dark belts are warm. Below it, the pattern reverses. Scientists have named this boundary the Jovic line, in analogy to the thermocline in Earth's oceans, where seawater transitions sharply from warm to cold. The discovery of the Jovic line provided new context for the Great Red Spot. The storm exists across this boundary, spanning the transition from one atmospheric regime to another. It is not just a surface phenomenon, it is embedded in the deeper structure of the planet. And the Juno team found something else. The vortices on Jupiter, including the Great Red Spot, are warmer on top with lower densities and colder at the bottom with higher densities. Anticyclones like the Great Red Spot show the reverse of this pattern at the surface, being cold on top but warm beneath. This inverted temperature structure is part of what keeps the storm stable. It creates a self-reinforcing loop of circulation that resists disruption. On Earth, storms are powered primarily by the condensation of water vapor at the base of clouds. That is what generates rain, wind, and lightning. Our hurricanes are ferocious, but they are shallow. They exist in a thin band of atmosphere, just a few kilometers deep. And the moment they make landfall and lose their source of warm ocean water, they die. The Great Red Spot has no such limitation. There is no land on Jupiter. There is no surface at all, just an atmosphere that gets denser and hotter the deeper you go, eventually transitioning into liquid hydrogen and, further down, into metallic hydrogen. The storm exists in a world without boundaries, and it draws its energy from somewhere far below the weather layer. Juno also observed two other large storms on Jupiter. Both had routes that extended past the cloud base, but neither went as deep as the Great Red Spot. This suggests that whatever is driving the spot is fundamentally different from what drives Jupiter's other vortices. Neptune has dark spots that appear and disappear over the course of a few years. They drift wildly in latitude because Neptune lacks the powerful jet streams that lock Jupiter's storms in place. Saturn has its own massive storms, but they tend to erupt in decades-long cycles and then fade. Nothing in the solar system behaves quite like the Great Red Spot, and yet, despite all of this, it is shrinking. When regular monitoring began in 1830, the Great Red Spot was more than twice the diameter of Earth, stretching roughly 39,000 kilometers across its longest axis. By the time the Voyager spacecraft flew past in 1979, it had gotten smaller, but was still enormous. An observation in 2004 measured it at about half the size it had been a century earlier. Today, the spot spans roughly 14,000 kilometers, still bigger than Earth. But the trend is clear, and the rate of shrinkage appears to be accelerating, losing about 580 miles per year. Some astronomers have speculated that the spot could dissipate within a few decades if this trend continues. Others believe the shrinkage reflects changes in its cloud coverage rather than the underlying vortex itself, and that the storm may simply be settling into a smaller, more stable form. Amy Simon of NASA's Goddard Space Flight Center, who has monitored the spot for over a decade through the Hubble Space Telescope's Outer Planet Atmospheres Legacy program, believes it will likely stabilize. She has noted that the spot is currently overfilling its latitude band relative to the wind field. Once it shrinks inside that band, the jet streams will hold it in place. In 2019, the spot appeared to be flaking at its edges. Fragments of the storm were spinning off and dissipating into the surrounding atmosphere. This fueled dramatic speculation that the spot was dying. But other scientists pointed out that these flaking events could be explained by interactions with smaller cyclones and anticyclones passing nearby. The Great Red Spot regularly absorbs smaller storms. Sometimes that process is messy. It does not necessarily mean the vortex is falling apart. At the current rate of reduction, if nothing changes, the spot will become circular by approximately 2040. Whether it will stabilize at that point or continue shrinking into oblivion is one of the biggest open questions in planetary science. But even as it shrinks, the Great Red Spot is doing something no one anticipated. Between December 2023 and March 2024, NASA used the Hubble Space Telescope to observe the Great Red Spot continuously over a 90-day period. This was not the usual annual checkup. This was a dedicated campaign designed to watch the storm evolve in near real time. What Hubble found was bizarre. The Great Red Spot was oscillating. Its shape was pulsing, squeezing inward and then expanding outward in a rhythmic 90-day cycle. The entire storm was jiggling, as NASA described it, like a bowl of gelatin. Amy Simon, who led the study, said that while scientists knew the spot's drift rate varied slightly in longitude, no one expected to see its size oscillate. As far as anyone knew, this behavior had never been identified before. This was the first time researchers had the proper imaging cadence to capture it. And with Hubble's resolution, they could say definitively that the spot was squeezing in and out at the same time as it was speeding up and slowing down. The observations revealed a pattern. When the storm drifts at its slowest speed, it reaches its maximum width and becomes brighter in ultraviolet light, suggesting less haze absorption in the upper atmosphere. When it speeds up, it contracts and dims. Mike Wong, a co-investigator from the University of California at Berkeley, compared the mechanism to a sandwich. As the spot accelerates and decelerates, it pushes against the jet streams to its north and south. The jet streams act like slices of bread. When there is too much filling in the middle, the bread bulges outward. The team also measured changes in the storm's wind speeds over the oscillation cycle. The maximum wind velocities varied by about 20 meters per second, roughly 45 miles per hour, over each 90-day period. That is small compared to the storm's overall wind speeds, but it reveals something important about the internal dynamics that no one had previously understood. And here is the part that makes it genuinely mysterious. There is currently no hydrodynamic explanation for this oscillation. The physics of fluid dynamics, as we understand them, do not predict a storm that breathes in and out on a regular cycle. Something deeper is going on. We just do not know what. The Great Red Spot also does not appear to follow a previously established relationship between its shape and its internal rotation, known as the Kida relation. This mathematical framework describes how elongated vortices should behave in a rotating fluid. The spot seems to violate it. Its behavior is more complex than the two-dimensional models can account for, possibly because the storm's three-dimensional structure and its interactions with Jupiter's deeper atmosphere introduce forces that our models have not yet captured. Simon's team has continued observing the spot since the initial 90-day study. They hope that additional oscillation cycles captured at Hubble's resolution will reveal other parameters that correlate with the breathing, potentially pointing toward the mechanism that drives it. For now, it remains one of the most unexpected discoveries in the recent history of planetary science. A storm that has been observed for nearly 2 centuries, and no one noticed it was pulsing until 2024. In July 2022, the James Webb Space Telescope turned its instruments toward Jupiter, specifically toward the Great Red Spot, and what it found upended one of the longest-held assumptions about the storm. Scientists had always believed that the upper atmosphere above the Great Red Spot was boring. Jupiter receives only about 4% of the sunlight that Earth does. Without strong solar heating, the upper atmosphere in this region was expected to be smooth, featureless, and homogeneous. There was no reason to expect complexity up there. Webb's near-infrared spectrograph looked at the region directly above the spot and found a stunning variety of previously unseen structures: dark arcs, bright spots, intricate patterns stretching across the entire field of view. The upper atmosphere was not calm at all, it was wildly active. Henrik Mellin of the University of Leicester, who led the study, admitted that the team had assumed, perhaps naively, that this region would be really boring. Instead, it turned out to be just as interesting as Jupiter's northern lights, if not more so. So what was causing all of this activity? The leading explanation is gravity waves. Not gravitational waves, which are ripples in space-time predicted by Einstein. Gravity waves are atmospheric phenomena. similar to the ripples you see when waves crash on a beach and reshape the sand. On Jupiter, these waves are generated deep in the turbulent lower atmosphere, all around the Great Red Spot, and they travel upward in altitude, altering the structure and emissions of the upper atmosphere as they go. These kinds of atmospheric gravity waves exist on Earth too, but on our planet, they are much weaker. On Jupiter, the energy being pumped into the upper atmosphere by the Great Red Spot is enormous. The storm is essentially sending shock waves through the sky above it, reshaping the ionosphere in real time. And this connects to an even older mystery. Jupiter's upper atmosphere is far hotter than it should be. Given the planet's distance from the Sun, temperatures up there should be relatively cold. Instead, they are comparable to what we see in Earth's upper atmosphere, where the International Space Station orbits. Scientists have called this the energy crisis of the giant planets. In 2016, researchers using NASA's Infrared Telescope facility in Hawaii found that the hottest region of Jupiter's upper atmosphere was directly above the Great Red Spot. The temperatures there reached roughly 1600 Kelvin, several hundred degrees warmer than the rest of the planet at that altitude. The proposed explanation is that the Great Red Spot generates two kinds of turbulent energy waves: gravity waves and acoustic waves. These waves travel vertically upward for hundreds of kilometers until they break in the upper atmosphere, like ocean waves breaking on a beach, converting their energy into heat. So the Great Red Spot is not just a storm, it is a heat source. It is actively warming Jupiter's upper atmosphere from below, through a process that we are only beginning to understand. This finding carries implications far beyond Jupiter. Many giant exoplanets orbiting other stars also have upper atmospheres that appear to be hotter than they should be based on the amount of stellar radiation they receive. If the mechanism observed at Jupiter, where deep storms pump energy upward through wave activity, is common among gas giants, then it could explain the thermal profiles of worlds we will never visit. The Great Red Spot may be teaching us something fundamental about how giant planet atmospheres work across the universe. Around the same time Webb was observing in near-infrared, its mid-infrared instrument was also pointed at the Great Red Spot. This instrument allowed scientists to peer past the colorful clouds and into the weather layer below. The goal was to build the first truly three-dimensional map of the storm's temperature, composition, and dynamics. What they found was a layer cake of complexity. At the top, the cold core anticyclone dominated. The Great Red Spot's interior was about 4 degrees cooler than its surroundings at a pressure level of 400 millibars, the altitude where the temperature difference was greatest. This cold anomaly extended upward toward the tropopause, the boundary between Jupiter's troposphere and stratosphere, before gradually fading away. But the map also revealed something that had been suspected for decades but never clearly confirmed. The Great Red Spot is tilted. The northern edge of the storm reaches higher into the atmosphere than the southern edge. The white collar of clouds that surrounds the spot is not symmetrical. On the north side, there is evidence of upwelling air, colder temperatures, enhanced ammonia, more phosphine, and denser aerosols. On the south side, the air appears to be sinking, with warmer temperatures and depleted chemistry. This north-south asymmetry was visible in the temperature data, in the aerosol distribution, in the ammonia abundance, and in the phosphine maps. Every independent measurement told the same story. The storm is not a simple, flat, spinning disk. It is a three-dimensional structure with a complex internal tilt. And then there were the hot spots. High above the Great Red Spot, in the stratosphere at about 3 millibars of pressure, the Webb data revealed a pair of localized warm anomalies. These thermal features were co-moving with the storm below, drifting in longitude at the same rate as the spot itself. The temperature contrast between these hotspots and their surroundings was about 5 to 7 degrees. Scientists believe these anomalies might be generated by atmospheric waves propagating upward from the storm. The Great Red Spot is a massive obstacle in the atmosphere. Air flowing past it could generate Rossby waves or gravity waves that carry energy into the stratosphere, producing localized heating. Similar hotspots were observed by the Very Large Telescope and, decades earlier, by Voyager. But they were not seen by every mission. Cassini did not detect them in 2000. The ground-based Texas instrument did not see them in 2014. This suggests the features may be sporadic, appearing and disappearing over time, but always at the same position relative to the Great Red Spot when they do appear. The implication is striking. The Great Red Spot is not just influencing the atmosphere at its own altitude. It is reaching up, through waves and energy transfer, into the stratosphere above. The troposphere and the stratosphere, normally treated as separate atmospheric regions, are coupled together by this single massive storm. The Webb mid-infrared data also revealed the internal wind structure of the vortex in unprecedented detail. By measuring temperature gradients at every altitude, scientists could calculate how the winds change with depth using the thermal wind equations. The results showed that the winds decay with altitude, as expected for an anticyclone. But getting the calculated winds to match the independently measured winds from Webb's near-infrared camera and Hubble's visible light observations required placing those observations at very different altitudes than previously assumed. Specifically, the Hubble winds had to be placed at about 1200 millibars of pressure, much deeper than the 500 to 600 millibars that scientists had traditionally assumed. And the Webb near-infrared winds had to be placed at about 100 millibars. The gap between these two altitudes is enormous, and it means that the visible cloud layers of Jupiter, the ones we have been tracking for decades to measure wind speeds, may actually be located deeper in the atmosphere than anyone thought. This single finding has the potential to reshape our understanding of not just the Great Red Spot, but of Jupiter's atmosphere as a whole. One of the most persistent mysteries about the Great Red Spot is also the most obvious one. Why is it red? No one knows for certain. The leading hypothesis is that an unidentified chemical compound called a chromophore is responsible. This material absorbs blue and ultraviolet light, giving the spot its distinctive reddish-orange color. Some laboratory experiments suggest it could be produced when ammonia-based compounds or acetylene are irradiated by solar ultraviolet light, forming complex organic molecules called tholins. The red chromophore appears to be concentrated in the center of the vortex, within the region enclosed by the ring of peak wind velocities. Webb's mid-infrared observations showed that this same region contains excess phosphine, a molecule that is normally destroyed by ultraviolet light at these altitudes. So how does the phosphine survive? The data offers a compelling answer. The Great Red Spot's thick aerosol layers may be shielding the phosphine from photolysis. The dense clouds act like a sunscreen, protecting the molecule from the UV radiation that would otherwise break it apart. And because the interior of the vortex is remarkably stable, convectively speaking, the phosphine has time to accumulate rather than being dispersed. This suggests a feedback loop. The anticyclonic circulation concentrates phosphine within the vortex. The elevated aerosol layers protect it. The stability of the storm prevents it from being mixed away. And the phosphine, in turn, may participate in photochemical reactions that produce the very chromophore responsible for the spot's red color. Ammonia tells a different story. Unlike phosphine, ammonia was not found in significant excess inside the Great Red Spot compared to the surrounding atmosphere, but its distribution was far from uniform. On the northern side of the vortex, where upwelling appears to dominate, ammonia was enhanced. On the southern side, where air is sinking, it was depleted. This pattern was consistent across both observation periods, separated by 18 days, suggesting it is a stable, long-term feature of the storm's internal dynamics. The team also searched for ammonia ice within a small convective storm northwest of the Great Red Spot, in the turbulent Wake region. Despite strong evidence of vigorous upwelling in that area, including elevated phosphine and high-altitude aerosols, no ammonia ice was detected. This was surprising. Theoretical models predict that ammonia ice should form at certain altitudes within Jupiter's atmosphere. But it almost never appears in the data. One possible explanation is that ammonia ice particles are rapidly coated by other chemical species within days of forming, obscuring their spectral signature. If true, the only places where ammonia ice could ever be detected are regions of extremely violent updrafts, where fresh ice is continuously lofted faster than it can be hidden. We have been looking for this ice for decades, and we keep not finding it. The elusiveness of ammonia ice is one of the small but nagging puzzles of Jupiter science. Theoretical models clearly predict it should be there at around 800 millibars of pressure. Spectral instruments are sensitive enough to detect it, and yet it has only ever been confirmed across roughly 1% of Jupiter's visible surface. The ice was first detected in disk average data from the Infrared Space Observatory, then mapped in the Great Red Spot Wake by Galileo, and later found by the Cassini and New Horizons missions in limited patches. But inside the Great Red Spot itself, despite all the upwelling, despite all the dynamic churning, no ammonia ice has been conclusively identified. The storm may be too stable, too well organized, to produce the kind of explosive convective updrafts needed to continuously expose fresh ice before it gets coated. And that is a strange irony. The very stability that keeps the Great Red Spot alive may be the same quality that prevents us from seeing one of the most basic products of its internal chemistry. So here is where we stand. The Great Red Spot is not the ancient storm we once believed it to be. It is likely a successor, born sometime around 1831, after its predecessor quietly disappeared. It extends hundreds of kilometers into Jupiter's atmosphere, far below the reach of sunlight, drawing energy from processes we cannot yet fully explain. It is tilted. It is asymmetrical. It breathes in and out on a 90-day cycle that no existing model of fluid dynamics can account for. It generates waves that travel upward through the atmosphere, heating the stratosphere and reshaping the ionosphere in ways we only discovered in the last few years. It is shrinking. It has been shrinking for as long as we have watched it. Whether it will stabilize or eventually fade away, as its predecessor apparently did, is a question that no one can answer yet. And the thing about the Great Red Spot that makes it so endlessly fascinating is this. Every time we build a better instrument, every time we get a closer look, every time we think we finally understand it, it shows us something we did not expect. The Voyager flybys showed us the cold core. Galileo found ammonia ice in the wake. Juno revealed the deep roots. Hubble caught it jiggling. Webb found chaos where we expected calm. In 2031, the European Space Agency's Jupiter Icy Moons Explorer, known as JUICE, will arrive at Jupiter. It will study the planet and its largest moons in extraordinary detail, and it will have the Great Red Spot in its sights. What will it find? If history is any guide, it will find something no one predicted. Because that is what this storm does. It surprises us, every single time. For now, the Great Red Spot keeps spinning, cold at its heart, warm at its base, red for reasons we still cannot fully explain. A vortex older than most of our institutions, yet younger than we thought. A storm without a surface beneath it, drawing power from depths we cannot reach. And every few months, it takes a slow breath in and a slow breath out, as though it knows something about Jupiter that we do not. We will keep watching, because that is what you do when you find something this strange, this beautiful, and this stubbornly mysterious. You watch, and you wait, and you hope the next instrument is good enough to ask the right question. Because with the Great Red Spot, every answer we have ever found has only led to another question. And that is exactly how science is supposed to work.